Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. So this is number 27 and I'm going to discuss the relationship between entropy and temperature. So let's see if we can come up with a general formula for temperature. Now in previous videos I discussed entropy, the second law, and temperature and heat. So I suppose if you look at those you're well set to watch this particular video. So entropy and temperature. Bottom line up front. The formula, bottom line up front, will be that temperature is equal to del U, del S, constant number of particles, and volume. In other words, I'm saying that temperature is the proportionality constant, or the slope of an energy versus entropy graph. Right? That's the bottom line up front. But I'm going to make it a bit clearer. So let's start. Let's say we know that the second law can be written in many ways. We can say that heat goes from hot to cold. Right? We can say it that way. We now know why it does that. We know that the reason it does that is because it needs to maximize the multiplicity. We know that life or nature requires the multiplicity to be maximized. And we know that in order to maximize the multiplicity, heat flows. That is how the multiplicity is maximized, and heat there as a result flows from hot to cold. So the second law comes from these probabilities, right? So, and we saw that it is the probability of heat flowing from cold to hot is 0. The probability of the system being in equilibrium at any other value other than an equal sharing of energy between all your particles is also pretty much 0. Okay, so the point is that your heat will flow from hot to cold because your nature wants to maximize the multiplicity, and it will stop flowing when exactly half the energy, or when all the particles have the same energy. So if there are 2 systems, you have half the energy between them. 3 systems will leave a third, and so on. So we can also say that we want to maximize the multiplicity, or we want to maximize the entropy, or we want to maximize the disorder. And you'll know from my video on entropy that I don't like using the term disorder, but I'm writing it there just because people will have heard it that way before. So that is what the second law is. Now, we've also said in video number 1 that we defined temperature, we defined it as being the property which is the same for 2 bodies in equilibrium. That's what we defined it as. But let's be honest, we also had a second definition, and we said it was the tendency, or the willingness, we'll say, of your body to, and this is important, spontaneously give up energy. That's what we defined temperature as. Now, why am I labouring the point? Well, because we're trying to get a relationship between temperature and entropy, so we should know what temperature is. And finally, we said that entropy, instead of dealing with multiplicities, which are enormous numbers, they are extraordinarily large numbers. We could say the entropy is the multiplicity, but because we want to deal with ordinarily large numbers, we take the natural logarithm of it. So we know that the entropy is essentially the total number of states. To make life easier, we said, well, let's take the logarithm of it. So it's a logarithm of the number of states. And as we'll see now, we add this factor of Boltzmann's constant, and you'll see why in this video. And see why we give it units of joules per Kelvin. Right, because of the units, of course, on Boltzmann's constant, or joules per Kelvin. So let's go. So what we see is that temperature is related to entropy, because when 2 objects are in the same thermal equilibrium, the total entropy has reached a maximum possible value. That's what we said. We defined one of the definitions of the second law. But also we said that temperature is the property which is the same between 2 bodies when they're in equilibrium. So temperature is related to entropy. Okay, I hope that's clear from those definitions. So let's just look at two bodies exchanging energies. We know that at equilibrium, the definition of equilibrium is that the rate of change of the total entropy with respect to energy in, let's say, one of the bodies, let's say A, is 0. In other words, we've maximized the rate of change. We've minimized the rate of change, it's gone to 0. We've maximized the total entropy, or maximized the total multiplicity. Something we've seen plenty of times, and if you want to draw it, it will look like a Gaussian like this. Okay, we know that when it gets to here, the multiplicity is maximized, therefore the entropy is maximized with respect to the energy in A, or the energy in B, or the energy in C. But we need to pick one of them in order to analyze it. So what does that mean? Well, let's just do a small bit of manipulation. Well, we know that the total entropy, we know that S total, okay, is equal to S in A plus S in B if we're talking about two bodies. I proved that in my video on entropy. So that means that what we actually have is del S sub A, del U sub A, plus del S sub B, del U sub, and this is important, so I'm going to write it in a different color, del U sub A, B with respect to A. And we know the answer is 0. Okay, and it's important now that we see it's with respect to A. However, we know that if the two bodies, if energy comes from A, well, and it goes into B. So as a result, we can say that del UA, if energy goes from A, or if energy is changed in A, well, it has to go someplace else, came from B. So del UA is minus del UB. Okay, and that should be quite intuitive to you. So as a result, we can rearrange this, and we can say del S sub A, del U sub A is equal to del S sub B, del U sub B. Okay, so we know that that is the condition for equilibrium between two bodies. Alright, so when two bodies are in equilibrium, the slope of their S, or entropy versus energy graph, is equal for both bodies. Alright, that's what this means. So I'm just going to rewrite this equation up here. We know that del S sub A, del U sub A is equal to del S sub B, del U sub B at equilibrium. Okay, so energy goes into the object with the steep S versus U graph and out of the shallow S versus U graph. Okay? So we can say that the steep slope has a high temperature and the shallow slope has a low temperature. So I think it's probably best to give us an example. So I'm sure somebody will, or some of you will have seen entropy versus energy graphs in the past, but generally they look like this. So okay, so I've been drawing them plenty of times. So here's U sub A. Okay, and let's say this is 100. You have nice round numbers, and let's say the total entropy, okay, goes to, I don't know, whatever value. It doesn't matter. Let's say this is S, and it doesn't really matter what the value is. Now, on the same graph, we're going to draw U sub B, and if that's the case, then 100 for U sub B would be over here. Now, we know when the system will be in equilibrium. Well, it'll be in equilibrium when it's at 50 units of energy in A and 50 units of energy in B. Alright, so let's say that they cross here. Let's draw the entropy versus energy graph for A first of all. So I hope this is clear. Alright, so let's say it starts at 0, so there's zero energy in A. Well, then the function might look like that. Okay, so the function, if it went from 0 units of energy to 100 units of energy, its entropy function would do this. So what will B's entropy function do? Well, it'll do the complete opposite. It'll do this. Okay, that's what B will do. So this is actually, I'll draw B in a different color. So this is A. of B is going to be in green. There's B. Okay, so we now know that that's what we're going to do. They join somewhere in about 50 units of energy, which is exactly half the energy, or an equal sharing of energy. So this is the entropy. That's the entropy of both A and B. So what will the total entropy do? Well, if you think about it, the total entropy graph will look something like that. Because, think about it now, this is the total entropy, which I'll see if I can do in, what color? Blue. Let's see if my blue works. I really should get new biros. Because this point here is maximum entropy, corresponding with half the energy shared between the two of them. Now let's just look at the slopes. Now we're going to start getting messy here. If you look at the slope, this has a steep slope, okay, and this is a shallow slope. Or sorry, the other way around actually. But we can see, if you look at it, that the slope actually will go to the slope will go to 0 up here. That's when the slope is 0, and the slope is 0 when it's at maximum entropy, or half the energy is shared. Alright, so that's your entropy versus energy graph. So let's finally get the formula we require to relate entropy, energy and temperature. So we know that S is equal to Boltzmann's constant times the natural logarithm of the multiplicity. Alright, so therefore del S, del U, holding n, the number of particles, and V, the volume, fixed, is equal to del K log omega, del U. Okay, now let's just look at the number or the units here. Well, the units of this, of the natural logarithm, are, well, it's dimensionless, so we get joules per Kelvin, which are the units on Boltzmann's constant, and energy, which is joules, so we get per Kelvin. Or what we could say is that the units of del S, del U has per Kelvin as its units, or del U del S has units of Kelvin. So finally what we say is that temperature, we define temperature equal to del S, del U, holding n and V fixed, to the minus 1. But for experimental reasons, it's actually more useful to write it in the following way, because it's often easier to evaluate it this way. Alright, so we can see that temperature, okay, so temperature is found by getting the slope of your entropy versus energy graph. So T is equal to del S del U, the inverse of del S del U, or del U del S. Okay, so temperature is your slope of your entropy versus energy graph, and that's how you get temperature. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.